Hello. In this video, we are going to talk about separable differential equations. Give you a little bit of a sneak preview into differential equations class, which is part of the calculus sequence. So a differential equation, the simplest way to describe that would be an equation that has a derivative in it. So I have a couple examples here. This first one, y double prime minus 2y prime plus y equals 0. It has a first derivative and it has a second derivative in it, making it a differential equation. The second example, I use the different derivative notation, dy dx equals xy to the 1/2. Also another example of a differential equation. Now what we want to be able to do is solve a differential equation. And we're only going to look at one way of solving them. In this class, you can take the differential equation course in a couple of semesters to learn a whole bunch of different ways to solve different differential equations based on their characteristics. But when I'm looking to solve one of these, the first question is, well, what does the solution actually look like? When I solve a linear or an algebraic equation, usually I get a number that is the solution to that equation. And when I plug that number in, I get a true statement. I get two equal things. With the differential equation, instead of a number, you get an equation that when you plug it and its derivatives into the original function, you get a true statement. You get two equal things. So let's take this second example here and see how we can determine whether something is a solution. It's a great way to be able to check your work. So I've got this dy dx equals xy to the 1/2. And let's suppose that I think that y equals x to the 4th over 16 is a solution to the differential equation. I can check this by taking y and its derivative, since dy dx is in the equation, and plug them into this equation and see if I get a true statement when I simplify both sides. So first thing I need to do is find that derivative dy dx. So the derivative of x to the 4th over 16, well, I'm going to do power rule here. Remember, I'm deriving. I know we've been doing a ton of integration in this class. So derivative means I'm going to be bringing that 4 out front and then decreasing the exponent by 1. So I get 4x cubed over 16, which reduces to just x cubed over 4. So now I'm going to take that x cubed over 4, replace dy dx in the equation with that. And then on the right side, I'll replace y with x to the 4th over 16, and then see what I get when they simplify. So replacing dy dx and y in the equation, I get something that looks like this. I can simplify the right side by taking the square root of that x to the 4th over 16. So that's going to give me x squared over 4. And then I multiply that by the x, and I end up with x cubed over 4 on both sides of the equation. So I got a true statement, which means this is, in fact, a solution to the differential equation. So that's what a solution looks like. How do I get to a solution, though? Well, as I said, we're only going to look at one way of solving that. We're going to look at separation of variables. And so only certain types of equations are separable. And so those would be the only examples where we could use this method. If the equation is not separable, then I would have to come up with some other method. So we say that a differential equation is separable if I can actually separate the variables. So if this is an equation in x and y, I need to be able to separate the x and the y's from each other. So much so that I could actually move everything with a y to one side of the equation and everything with an x to the other. And that includes the differentials, the dy and the dx. I can separate them. I can treat them like a fraction, multiply the dx over to the right side, and divide the h of y over to the left. And I have separated the variables. So this is the criteria in order to use this method. If you can't separate it like this, then we're dead in the water. We can't use this method. We'd have to come up with another one. Okay, so let's see how that works. We're going to take equations, separate the variables, and then see, well, what do I do next to solve it? So here's an equation, kind of a nasty looking one. I've got x's and y's in there. I want to see if I can separate the variables. Now, before I do that, though, notice that I have this extra piece of information over here. It says y of 0 equals pi over 4. This is what we call initial conditions. And so we're not going to pay attention to those until the end of the problem after I've solved this equation, and then I'll show you what we can do with those initial conditions. So first up, separate the variables. So I'm trying to get y's on one side and x's on the other. I'm going to start by taking that cosecant of y and just subtracting it over to the other side. So now I've got cosine squared of x dy dx equals negative cosecant of y. So let's get rid of the fractions. I'm going to multiply the dx over to the right side of the equation. Okay, so it's looking better. I mean, I don't know how many fractions. I've just got the two terms on separate sides, but the x's and y's, they're all jumbled up. So if I divide the cosine squared x over to the right side, that would move all the x's to one side. And also the dx would now be in the numerator. I can't have the dx in the denominator. That's problematic for what I do after I separate the variables. Same thing with the dy. I want those differentials to be in numerators, not denominators. So it kind of determines which side things go to. Okay, so I'm going to divide the cosine squared x. And while I'm at it, I can divide both sides by negative cosecant of y as well. And that will have my variables all separated out. Now, everything with the y is on the left, everything with an x is on the right. So that's step one, is separate those variables. Now that I've done that, I can integrate this. Specifically, I can integrate the right side and the left side. If these two statements are equal, then the integral of these two statements must also be equal, save for a constant of integration. Okay, so I slap on my integral symbol for both sides of the equation. I'm integrating with respect to y on the left and with respect to x on the right. And looking at how would I integrate that, it actually makes my life easier if I use a reciprocal identity from trig. So 1 over cosecant is actually sine, and 1 over cosine is secant. So this actually simplifies things a little and makes it easier to integrate. So now I can integrate the negative sine of y on the left, and secant squared x happens to be the antiderivative of tangent. So I end up with this here. So cosine of y equals tangent of x plus c. Now you notice I only have one constant of integration on there. That one counts for each constant of integration you get on both sides. We've effectively just combined them and moved them to one side of the equation, which is a standard thing that we will do with this technique. Now, usually at this point, if I can, I solve for y. Because that's inside of a cosine, there's going to be issues with throwing in a cosine inverse there because of the domain restrictions on cosine inverse. So I'm going to opt to actually just leave it like this. But if I can, I do try to solve this for y. It's just not always going to be possible. So if I hadn't been given those initial conditions at the beginning, I would be done. This is my solution. It's what we call a family of solutions because that c could be any number of constants. I don't have enough information without initial conditions to know what that constant is. With this problem, though, I can take it a step further because I was given those initial conditions. So what I'm going to do is take those initial conditions and plug them into this equation. And so this is telling me y of 0 is pi over 4. So that means that y is pi over 4 and x is 0. So I'm going to plug that in to my solution. So cosine of pi over 4 equals tangent 0 plus c. And now I'm just down to the one variable, the constant. The c there is the only thing that I don't know. So I can simplify this and solve for it. Tangent of 0 is 0, so that I can drop out. And cosine of pi over 4 is root 2 over 2. And yes, we do want to see exact values there. So I found my constant of integration, and I can go ahead and plug that back into my solution in place of c to get a particular solution. So cosine of y equals tangent x plus root 2 over 2 is the particular solution given these initial conditions. And that is how you solve a separable equation using separation of variables. Now, before we move on, here's an example to try on your own before class.